Hey folks, this is my overview video to go along with assignment 13. This is where we start looking at calculus as more as a set of tricks and procedures used to find derivatives. That's kind of always going to be our main goal, is to find derivatives, but the limit definition of the derivative is a little bit awkward, hard to work with. So people have developed a whole bunch of procedures that in various situations will let you get the job done without having to appeal to the limit definition. Having said that, the first thing I want to do though is to give you one more example of doing that using the limit definition to find a derivative. So I've wrote it out previously, but let's unveil it a little bit at a time. The function that we want to work with, or that I want to work with in this example, is 1 over x. F of x is 1 over x, and we're asked to find f prime. So first, and this step, it's always the same if you're doing this limit definition, you write down the definition. You write down that f prime can be expressed as the limit as h goes to 0 of a difference quotient. Okay, but now we were talking about the function is 1 over x, so writing this thing generically is kind of strange. We should stick the function 1 over x in where the f's are. That's what I've done in this next line. 1 over x plus h minus 1 over just plain x divided by h. So that's a little bit of an algebraic challenge, isn't it? It's always weird and hard to work with something where there's fractions within fractions, which is why I like to do it that next step, which is instead of dividing by h, think about this as you're multiplying by 1 over h. And now we've just got sort of numerator and denominator, not numerator and denominator and other denominator, right? So that it's conceptually easier to think about it here. Okay, well, almost there. We still have a problem of we need to find the difference of these two fractions inside the big parens, and they don't have the same denominator. So what do you do with a thing like that? You find a common denominator, which is the product of the denominators in the two things. You know, it's x and x plus h here. How did that actually happen? In order to make the denominator be the product of those two things, I need to times the one on the left by x in the top and the bottom, and the one on the right by x plus h in the top and in the bottom, which is what I've got here. The numerator of the left-hand fraction just becomes x. The numerator of the right-hand fraction becomes x plus h. Now both of them have denominator, the product of those two things. So we've got a common denominator, great. Notice what's going to happen next is this numerator cancels. So you've got an x and then you're subtracting an x. There will be, the h will sort of survive that cancellation process. Let's see where we get. In fact, yeah, it's negative h that you end up with because we were subtracting x plus h. Huh, all right, well, wait a sec. See how there's an h in the numerator and an h, or 1 over h out here? Those things will cancel. We end up with negative 1 over x plus h times x. And now that, you can plug in h equals 0 into that, and it doesn't cause any problems. You don't get the division by 0 error because, well, when h is 0, this thing just becomes an x. So when h is 0, you've got x times x in the bottom of that fraction. We've evaluated the limit there, and you get negative 1 over x squared. So just to beat a dead horse to death, what we've done is take the derivative with respect to x of 1 over x, and we got negative 1 over x squared. That's the third view of differentiation that I've talked about, thinking of it as an operation that you do with one function as the input and another function as the output. One thing that is kind of interesting to do is write both of these things in terms of negative exponents. Some folks talk about this as the calculus-friendly way of approaching a thing. 1 over x is the same thing as x to the minus 1. And this one would be negative x to the minus 2. One of the things we're going to look at today and really do it, which I told you about last time, is the power rule. The power rule says multiply out front by the power and then reduce the power by 1. You see how we've got a minus 1 out front, and then 1 smaller than minus 1 is minus 2. So this is another example of the power rule. Okay, so well, we should head in that direction. Before we jump though to the rules, there's some very, very basic derivatives that you can figure out without having to do any real work at all. And so I want to show you those. The first one is differentiating lines. That is something where you have f of x looks like mx plus b. Well, then what's f prime going to be? I'm claiming this is something we can work out without even doing any computation. We need to think about this just in terms of what does the derivative mean. Okay, well, the derivative is the slope of the tangent line. But this thing is already a line. So that thing is its own tangent line. Any point on it, if you want to have a line that passes through that point that goes in the same direction as the line, well, you're going to have slope m. So it's not an unknown question mark, it's m. That's what the derivative is. That's kind of cool. If you have a line of slope m, it doesn't matter what b is, you just get m. Now, another, maybe a consequence of what we just did is to think about constants. Suppose I had f of x is just equal to some constant k. Never changing, this, like f of x equals 3, just a number on the right hand side. Well, then that's like a line, isn't it, where the b is k and the slope is 0. The horizontal line has slope 0. Setting f of x equal to a constant, its graph would be a horizontal line. Well, what's the derivative of that? It's the same answer. You take the slope, but the slope was 0. So here f prime of x is a constant function that's always 0. Now that's sort of nice. It tells you that constants just die when you run them through the differentiation ringer. If you have just a number, take its derivative, you get 0. It kills it. If you have something times x, it no longer has any x in it. So in a way, that gets knocked down a notch in the hierarchy of difficulty of functions. But just a plain constant gets all the way down to 0. Okay, so those are the no computation examples to think about. The equations of lines turn into just give you their slope, and if the function is a constant, it just goes to 0. There's some very simplistic rules that we can use, and I'm not going to worry too much about arguing why these are the case. It's just something that I want you to know about because you'll just use these facts. So maybe I should say simple facts about derivatives, because I'm not going to prove them. The first one is if you have two functions added together and you want the derivative of that, you want to prime that sum, all you have to do is prime the things individually and go ahead and add them up. The way they write this in the book is a little different, and I should probably write it and just show it to you. They say if you're taking the derivative with respect to x of this sum, that you can do what's on the right hand side here. You get f prime of x plus, g prime of x. And while that's, I understand why they wrote it this way. This is sort of like mixing apples and oranges. See, they've used the Leibniz notation on the left, and then they've used the Newton-style notation on the right. So it's a little off. But, you know, these notations are interchangeable, so you can go ahead and mix and match them. It feels like strangeness to me. It's like somebody asked a question in English and I responded in French. You know, that would be weird. All right, so that's a first example of a simple fact about how derivatives work, and this is called the addition rule. Very imaginatively named thing. There's also the subtraction rule. How's that look? Turn that plus and that plus into a minus. So we also have the subtraction rule. It's really two rules for one. Make that a minus, that a minus. Let's see, these would be minuses. That's the subtraction rule. In a certain sense, you know, I like to point out that there is no such thing as subtracting. Really, what you're doing is adding a negative number. And that might be a better way to say it. Sums and differences, they're the same operation, really, just with a minus sign thrown onto one of the pieces. So it's kind of enough to talk about the addition rule. But anyway, in the book, they also give you the subtraction rule as a separate thing. The other factoid that we should know is, what do you do if you have a multiple, a constant multiple of some function? And a thing like that, a multiple of the function, needs the derivative. Now this, I think, is almost obvious. If you had f of x and you knew what its tangent lines were like, and then you scaled it by this factor of k, made it taller or made it shorter if you want. It depends on what value k is. You could turn it upside down if k was negative. What effect does that have on the slopes of tangent lines? Well, if you imagine the graph of f of x just sort of being morphed, you know, stretched out, all of its tangent lines are going to get stretched out too, and they'll get stretched out by the same factor. So that's maybe makes it reasonable to say, well, okay, we should just scale the derivative of f by the same factor if we're looking for the derivative of the scaled version of f. And that's right, that's what you do. So this is called the constant multiple rule. It's important that the modifier constant is in there, because if you multiply by something that's a function, then this doesn't work. It's just something numeric, right? An actual number out front that you can put it through the argument we had. If you had a f of x times g of x, you actually have to do something different. There is a rule for that too, but it's coming later. Okay. One thing I want to point out is these things look like rules of algebra. This one, for instance, the addition or subtraction rule, looks like you can just distribute that prime across a sum or a difference. And this one looks like, well, if you've got constants in the thing that's being primed, you can just pull them out. You can undistribute or factor out a constant. So both of these things can be viewed as algebraic operations that are valid to work with the derivative. Okay, so our last task for today is to see the power rule. To do the power rule, we really just need to figure out the algebra of powers of things like x plus h. Let me illustrate that. Do you remember when we were working out that x squared, when you took its derivative, gave you 2x? There was a bunch of algebra in taking that limit, you know, using the definition, but the big thing was that we needed to take x plus h and square it. And you had to FOIL rule that, and it came out as x squared plus 2hx plus h squared. So here's what we're going to need to do to figure out how to deal with powers in general. We're going to have to look at different powers of x plus h and try to deduce the pattern. Now the best way to do that is, I mean, I can actually teach you how to take powers of things by hand, but I think it's quicker and just simpler if we transition to using Geogebra. And I will, oh, there we go. So here's the Geogebra window. This is the starting point for Geogebra, and normally we just go over here and click the Start Calculator thing. But I want us to use the Cas Calculator instead, CAS Calculator. See where I'm pointing? That stands for Computer Algebra System. And it kind of looks the same. Maybe there's slight details that are different. But you get some different capacities in the Cas than you did in the other one. One of which is this double dot menu, which has all the different computer algebra system type operations you can do. I believe the one we want is in the algebra subsection. It's called Expand. So what this will do is take something like x plus h to the second power and square it, and foil it out for us. Let me show you. Type expand. It does do tab completion if you want. And then I'm going to go ahead and give it x plus h to the second power and see what it does with that. Well, it did the right thing, but do you notice how it wrote it in reverse order? It's because it thinks that h is the smaller, or the first variable, because it comes earlier in the alphabet than x does. So just read this right to left. Think of it as x squared, 2hx, h squared. Those are the terms, reading right to left. Now, the reason I bring this up is, well, what if we wanted to do the third power of x plus h? How would that look? Expand. Sorry, I can't type. Expand x plus h to the third power. Dang. Now that's more complicated, but it's not terrible. It's x cubed, 3hx squared, 3h squared x, and h cubed. I'm gonna copy that onto our paper version of things. I had just worked it out, and it was that x plus h cubed was x cubed plus 3hx squared plus 3h squared x plus h cubed. And both of these expansions have the same pattern going on in them. The power of x starts out at the same as whatever the power you're raising is. I was talking about the pattern here. You start at the highest power, x. This is the cube of x plus h, so it begins with an x cubed. And see how the powers on x go down? We have x cubed, then x squared, then that's really x to the 1 power. And honestly, you could have an x to the 0 power here, because that's a 1. So, okay, nobody would write that, but you could. So it goes 3, 2, 1, 0. Conversely, the powers of h go up. 0th power, first power. Right? This is h to the 1, h squared, h cubed. Let's transition back to Geogebra and get ourselves a 4th power. In fact, you know what? I can just edit this one. Just take that 3 and make it a 4. Let's see what it tells us. I guess we're going to need to see more of it. Yeah, it's a little bit short, or it was a little short. 8. Well, okay, I'm going to read it backwards. X to the 4th, 4hx cubed, 6h squared x squared, 4h cubed x, and then h to the 4th. Let's, again, put that on paper. X to the 4th plus 4h x to the 3rd plus 6h squared x squared plus 4h cubed x plus h cubed, h to the 4th. Perhaps I should have done this. I imagine that's not there. What if we filled in above this x plus h to the 1st power? Well, that would just be x plus h. And indeed, we could go one step before that, x plus h to the 0 power, and that would be 1. Now, a very smart man named Blaise Pascal, who's often better known for his thing known as Pascal's wager, which was about the existence of God. He was a philosopher as well as a math geek. He was very interested in probability, and it turns out that this is the kind of thing you need to do for certain probability problems. And he looked at these expansions we've got and realized, you know, you got that easy pattern in the powers of x and h in each of these things. What's important is the numbers that come up front. So he pulled out the coefficients from this thing and he put them into a triangle. And this is hence known as Pascal's triangle. The first 3 rows, although people number the rows starting at 0, so that will be row 0, row 1, row 2. The row 3, really the 4th row, but we call it row 3, is the one where we take the coefficients of our cube thing there. And those go 1, 3, 3, 1. And finally row 4, 1, 4, 6, 4, 1. You might want to do a 5th power or something, but I mean, when Pascal was doing this stuff, they did it by hand. They didn't have a Geogebra to turn to, so raising a 5th power was kind of a big deal. But if you did, this is the numbers you would get out of it as in the coefficients of the expanded 5th power. 1, 5, 10, 10, 5, 1. Now, I'm not that smart that I can 5th power something in my head, trust me. But I do know the pattern that builds this table, and it's actually real simple. You see how you got this sort of lines of 1s on the outside? Every number that's on the inside, you just add up the things that are above it on either side. Like that 2 is a 1 plus a 1. Or this 4, that's a 3 plus a 1. The 10 right here, that's a 4 plus a 6. So you can build up Pascal's triangle to as high a power or as high a level as you want, but for our purposes, it's interesting to notice what's going on with these numbers right there, the sort of inner diagonal of it. Because these guys, the 1s on the out front, those are the coefficients of x to the whatever power we're at. These guys are the coefficients of what we want. 4hx cubed, for instance, that 4 comes from right there. So this diagonal one in from the side of the triangle contains the coefficients. We're looking at the different second term with its limit as h goes to 0. Why do I care about those? Well, the first term, remember how the difference quotient worked? Let's stick with using k as the power. H to minus some power, k. And then minus just plain x to that power? Well, so the first term and that x to the k, they're going to knock each other out. Expand that out and subtract the x to the k. So this is the highest degree term of what remains. And you should also notice that everything after that has lots of h's in it. H squared, h cubed, so however many powers of h times h, but the h will cancel. This is the one that sort of survives when we do the limit as h goes to 0. Because this one h gets canceled with the h at the bottom. I've thought about canceling the h with the other stuff. You just get 4x cubed when you're taking the derivative of x to the 4th. You don't have an h in the thing anymore. The things we're looking at here on the inside of the edge of the Pascal's triangle. Now, honestly, usually people write this in terms of that tells us the things that will survive when we're taking a derivative by the limit definition. Well, the same algebra that happened here. The n comes out from x plus h to the 5th power. That was a power on x goes down by 1. And when I was raising x plus h to the 4th power, I'm just changing k's to n's to make that. So this kind of that's the power rule. Pattern matching. We don't need to be too completely precise in the thing, but if you take x plus h to the k power, it's going to start with x to the k. The next term is going to be k times x to the k minus 1, and then there's other stuff that you don't care about because it's got h's in it. And when you divide this whole thing by h, remember again, there was the minus x to. Okay, I probably should be a little more accurate about this. So let me start a new sheet. Okay, yeah, I'm going to be a little more careful about how we derive the power rule. But what we're looking for really is the derivative of x to the n. And the limit definition tells us this. You should take limit with h going to 0 of x plus h to the n power minus x to the n power, all divided by h. And we just saw that this expansion of x plus h to the n, well, at least we know what the outline is. We know what the first several terms are. It starts with an x to the n, then there's a n times x to the n minus 1 times h, and that's kind of as much of it as I care about, because everything else is stuff with h squared or higher. Now, that seems like weak algebra, but this is going to be valid because, well, the other piece of that is you're going to subtract x to the n and then divide through by h. So when we subtract the x to the n, this x to the n is gone, right? Those two terms knock each other out, and you end up with limit h goes to 0 of, let's copy the first one, n times x to the n minus 1 times h, and then just say stuff. That's the stuff that has h squared or higher in it, all divided by h. And when we cancel this stuff that has h squared or higher with the h that's down below, there's still h's in that, but not this term. That term, there's one h and it goes away. So we get the limit n times x to the n minus 1 plus, let's say it this way, stuff that still has an h or more. But it's enough that it has a single h in it, because what happens when you take the limit with h going to 0? All of that other junk goes to 0. So we finally can evaluate the limit, and you get, wait, you're evaluating it, so you don't need to write lim anymore. You get n times x to the n minus 1. Now that's the power rule. There are two other strange derivatives that they include in this section, and it's a little odd that they do, but while we're here, let me just mention them. They also mention we know how to take the derivative of e to the x. And the reason we know how to take the derivative of e to the x is e was actually constructed so that this trick would happen. This literally is what makes e natural in terms of using it as the base for natural logs. If you take the derivative of e to the x, you just get e to the x. There's not too many functions that happens with. If you take the derivative of 0, you'll get 0, but that's kind of a weak case. E to the x is interesting. It's the slopes along it are the same thing as its values. The other one they took the derivative of, which is an oddball, is the natural log of x. And this is just one to remember. Log of x's derivative is 1 over x. Watch out for one thing, though, with this. The natural log is defined only for numbers to the right of 0, for positive numbers. So we should really say the natural log's derivative is 1 over x with a restriction on its domain. X has to be greater than 0. All right, that's our toolkit for now. We've got the sum rule, the difference rule. We've got the power rule, which is really handy. This thing about e to the x and this thing about log x. There's, what did I just name? 6 things? It's surprising how much this will let us get away with. So for let me just show you an example of taking a derivative of something pretty complicated, but it works out to be easy enough. Suppose I had 3x to the 9 plus x to the 6 minus 1 over x, I'm sorry, I was getting ahead of myself, minus ln of x, and then plus 2e to the x. That's a crazy expression. I'm only doing that as an example. Nothing like that would ever turn up in a real-world problem. But You want to take its derivative? Not a problem. This, first of all, the overall picture here is we've got a function plus another function minus another function plus a fourth function. These things are separated by pluses and minuses, and the derivative works just fine on it. It distributes across the pluses and minuses. So you can write this as 3x to the 9 prime plus x to the 6 prime minus ln of x prime plus 2e to the x prime. Okay. Then primes, when there's a number out front, you can just pull that number out of it. In the book, they say the number just goes along for the ride. I kind of prefer to think about it as you can pull it away. It can be factored out. It leaves and stays behind when you take the other thing for the ride. So we have 3 times the derivative of x to the 9. Okay, that one doesn't need anything. I'm just going to copy it, x to the 6. Neither does the log. Both of these still need their prime on them. And then this one's got a constant we can pull out, 2 times e to the x's derivative. I guess I'm going to not try to crowd this into the bottom, but we'll move it up the screen a little bit so we can see it. All right, the next step is using either power rules or some of the other things I mentioned, e to the x and ln x. X to the 9's derivative is 9 times x to the 8. That is, remember, you take the exponent, sticker out front, and then reduce the exponent by 1. The next guy's derivative is 6 times x to the 5th power. That one is the special case I mentioned. Log's derivative is 1 over x. And the last one is 2 times something's derivative, but e to the x is the other nice one that's pretty cool. It just is its own derivative. I think about the only thing else I can think to do here is maybe combine some stuff. That would really be 27x to the 8 plus 6x to the 5th minus the 1 over x and plus the 2 e to the x. So yeah, while we would never encounter something that ugly in the real world, it's kind of comforting to know that you can deal with such a thing if you need to. All right, so that's a wrap for today. Have a great rest of your day.